before I get into talking about the homework answer key. So I think I got homework submissions from everybody, and I graded everything that was submitted. And then I posted the answer key already for chapter 1. However, I want to spend a little time going over it before we proceed further in chapter 2. So let me find my share screen here. All right, so the beginning of the homework starts with a little back and forth conversion between milliliters and liters. Remember that this is a 3 decimal place move. When you do the first one, you are going from milliliters to liters. So you are dividing by 1,000. This will give you 1.375 liters. When you are doing the second half of that question, you are going in the opposite direction. You are starting with liters and you are going back to milliliters. So multiply your 0.067 by 1,000 to give you 67 mils. The next segment just gives you 4 different numbers and asks you how many sig figs are present. You must make use of the sig fig rules in order to answer these questions correctly. Looking at the first one, you have 4,260. Note, there is no decimal point, so you are supposed to assume that the 0 at the end is not a significant figure. This is why there are only 3 sig figs. For the number 900, again, there is no decimal point displayed in the number. Only the 9 is considered to be a significant figure. That I gave you a number that was much smaller than 1. Your zeros at the beginning are leading zeros. Therefore, they are placeholders and they do not count as sig figs, only the 3 and the 7. So that one only has 2 sig figs. And then the last one, I did give you a decimal point, despite the fact that there are some zeros in that number. Presence of the decimal point indicates that you need to count all of the trailing zeros. So there are 4 sig figs. In grading, I noticed that there were a number of errors in doing the math problems for number 3. Most people did the math part of it correctly. However, a significant number of people did not apply the significant figure rules for calculations after the calculations were made. When you add the first 2 numbers together, 956.3 and 8748.004, your calculator will tell you 9,704.304, but according to the rules of sig figs, you are only allowed to report your answer with the least number of sig figs that were in the calculation in terms of decimal places. Therefore, you can only report your answer as 9704.3. You cannot include the other 2 digits. For the second problem, multiply 64 times the exponent base number of 3.69 times 10 to the 4th. Your calculator will give you 2,361,600. You are only allowed to report your answer to 2 sig figs. You could insert zeros after the 2 and the 4. However, the most efficient way to express your 2 sig figs are to write it as 2.4 times 10 to the 6th. You cannot give me all of the numbers, only the 2 and the 4. For the third one, you have 787.667. So there are 6 sig figs in that number, but you are dividing it by 48. There are only 2 sig figs in that number. Your answer is only permitted to have 2 sig figs. Your calculator is going to give you a lot, 16.409729. You must round it all the way down to 16 so that your answer only has 2 sig figs. And the final one is another one, since it's subtraction, that focuses on the how many decimal places are you allowed to report. 365.2, so that's a single decimal place. You are subtracting 41.003, 3 decimal places. Your answer is only allowed to have 1 decimal place. So after you crunch it through your calculator, you must round it to 324.2. These were each of those was a 2-part question. Not only do you have to do the math correctly, you also had to apply the significant figure rules also. Then we have 2 one-step conversions, 75 meters. Obviously there's plenty of sources on the internet, but there's also that really useful appendix in the back of your lab book, Appendix A, which has lots and lots of conversion factors for you. Your 75 needs to be multiplied by 1.094 to give you 82.05 yards. This one I did not request appropriate sig figs for, so as long as the math was correct, that was fine. 11 ounces and 1 gram is 0.03527 ounces. So you are dividing, if you use this particular conversion factor, 11 ounces is 311.88 grams. Then we have a couple of multi-step conversions. So a dirigible, a blimp. You can blame my son for this particular problem. He was playing a D&D game with some friends of his, and they were having an argument about how long it would take for their blimp to go a certain number of miles over the terrain and all sorts of like that. So he had all of these pieces of data at his fingertips, and he wrote this problem, and I thought it was really cool. So we've got a 250-gallon tank, and this gets really crappy gas mileage. We have 8 miles to the gallon. But that does mean, because the tank is large, that you can go 2,000 miles on a full tank. It then asks you as a separate part of the question, how many hours is it going to take you? So not only is this a gas sucker, it also doesn't travel very fast. 450 feet per 12 seconds, but you need to convert that into miles. I did this or miles per hour, basically, so that you can figure out how many hours you have. So I took my 450 per 12 seconds. I then converted it over with 3,600 seconds per hour, and 1 mile being 5,280 feet. It puts along at about 25.5 miles an hour. But if you're going 2,000 miles, it's going to take you a little over 3 days, 78.2 hours to burn through that full tank. Unit conversion is just unit conversion. It doesn't matter whether you are going back and forth between various metrics, between English system and metrics, or in this case, this pretty much used entirely English system. So as long as you know your units and your conversion factors, the math applies. Converting to temperature readings to another unit. We have 550 Fahrenheit, kind of broil temperature. You need to subtract your 32, because it's what's inside your parentheses, and then multiply by your 5/9. That will give you 287.8 Celsius. Then add your 273 to turn it into Kelvin to get 560.8 Kelvin. -17 Celsius, converting over to Fahrenheit, first must be multiplied by the reverse fraction, 9/5, and you still have a negative value at that point. You have -30.6 Fahrenheit, to which you can then add, or Celsius rather. No, that is actually, I haven't even finished the conversion yet. Anyway, it's -30.6. Add your 32 and you get 1.4. Because remember that there's quite a big difference between where 0 is on the Celsius scale versus where 0 is on the Fahrenheit scale. There's quite a big space in terms of the size of the units. All right, then I gave you another volume density math problem here for steel deck plating. I got some unrealistic answers. Think about this. Okay, one of the things that I mentioned, we were talking about density as standard sort of ways of looking at data. One of the things I told you is that normal average everyday items, a piece of steel is a fairly average everyday item, can't have values greater than 30. I had a few answers that were in the hundreds of grams per cubic centimeter and a few that were in the thousands of grams per cubic centimeter, which is kind of neutron star level density. So think about the realism of the numbers that you are examining. This is a tile, okay? It has 1 foot wide, 1 foot long, but it's only 1/4 of an inch thick. I converted it, each of my units, over to centimeters, and then I did my 3 units multiplied together. You don't have to do it this way. You could have done it as do your multiplication first and then convert it. It would not give you a different answer. Your volume of your steel deck plate is 589.9 cubic centimeters. You have 10.2 pounds. I used the rounded version when I did the answer key for this, 2.2 pounds per kilogram. So this steel deck plate weighs 4.64 kilograms, which I then need an additional step for. I need to multiply it by 1,000 grams per kilogram because I want my final density to have the units of grams per cubic centimeter. I think everybody's done lab for the first cycle at this point. One of the things we did in lab was to do the density of some little metal cylinders. Your answers should have been probably greater than 1 gram per cubic centimeter, but definitely less than 15 grams per cubic centimeter, because I think the densest item that was provided was brass. Even that does not exceed 15 grams per cubic centimeter. And since we're coming on here on the tail end of the pandemic, and when I originally designed this answer, this homework set, hoarding of toilet paper was just oh so very much a thing. So I had you calculate the volume of a roll of toilet paper. Again, I had a couple of people give me answers that could not possibly be true. 1 cubic centimeter is about the size of a standard little 4x4 Lego brick, okay? So a roll of toilet paper very definitely has to be bigger than 1 cubic centimeter. I gave you the density. I gave you a mass. Rearrange your equation such that you are dividing your 227 by the density to give you 1,576.4 cubic centimeters. All right, scientific notation comes next. Make sure that the numbers out in front of your times symbol are between 1 and 10. I had a few people who gave me exponential notation that was not scientific notation. Oh, and my son is handing me a Lego brick.
Which is about,
okay, and I think I'm about right.
It's
okay.
1.5 by 1.5 by 1.
So this is slightly more than 1 cubic centimeter. Okay, 1 cubic centimeter is not very big.
Mhm.
All right, so yeah, make sure your numbers out in front have to be between 1 and 10. You will end up with 3.4 times 10 to the 4th, because it is a large number, therefore a positive exponent. And then I gave you a small number, and you should have 9.1 times 10 to the negative 3rd. You must have a negative exponent because it is a number less than 1. The last few problems are sort of concept oriented. Cobalt compounds being pink is qualitative. It has no number values in it. A graduated cylinder containing 46 milliliters. That one is quantitative because it does have a number value present. I gave you one that asks you to decide between heterogeneous and homogeneous. Okay, vehicles on Granby Street, just because the building for lab where lab is held is on Granby Street. Obviously, there's probably some cars, the occasional truck, the occasional motorcycle, a few bicycles. So heterogeneous for that. Mountain Dew soda. This is why it says don't overthink. I had a few people who declared this to be heterogeneous. Hopefully not, okay? A soda is basically the same all the way through. My cat is being obnoxious. And also the final item there, literally, the word solution is supposed to be your tip-off. The definition of a solution is a homogeneous substance where one thing is dissolved in another, with a typical solution being a solid dissolved in a liquid. So go back and if you had errors, go back and have a look at the answer key, compare your answers and figure out where your mistakes were. Are there questions about the homework set? All right, we are going to plow onward toward more of chapter 2, which give me a minute. I have to switch files. I'm going to close my homework file and find my notes file for chapter 2.
Some little bits on the muffins are bubbling.
That's fine.
Yeah, hopefully the liquid will melt away, or evaporate away, I should say.
All right. Periodic table. Okay. Granted, I have a bit of a glare because it's plastic. So this is the upper left-hand corner here that has a hydrogen. There are vertical columns, which are one of the things we were talking about toward the end of class on Tuesday. There's rows going across this way. Over here in the far right-hand column is a helium. All of these are different columns. And then there's these two separate lines at the bottom, which actually insert into a spot up here, because in fact, that would make the table very, 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 very wide, which is why traditionally they are pulled out and written at the bottom to make it easier to print on one page. All right, so let's talk about the organization a little bit. So we are focusing for the moment on the ones that have the Roman numeral and the letter A. We're going to ignore hydrogen for a moment because hydrogen doesn't follow the rest of the rules of the group 1 elements. We're going to start with lithium and go down the column. So lithium, sodium, rubidium, cesium, and francium. This column has a name. They are known as the alkali metals. They have certain things in common. They all have relatively low melting points. Some of the ones lower down on the periodic table, like rubidium, cesium, and francium, if you put them in your hand, not that you would really want to do this, but if you did, they would melt almost like an ice cube melts in your hand. They do not stay a solid at slightly warmer than room temperature. They are also soft. Soft, however, is sort of a relative definition. Let me tell you a little piece of reality. So we purchased some sodium for the lab for the purpose of doing some demonstrations. And because the other line down there, that they react with water, they are stored in either kerosene or mineral oil when you are not using them. So it was shipped to us and it was kind of in a rectangular block, almost like a block of butter. And we figured, oh, well, we want to store it in a jar. Okay. We'll just grab a couple of those metal spatulas like you guys were weighing in lab this past week, thinking that like butter, all you have to do is just sort of push down a little bit, and you can cut these soft metals and then place them in smaller containers so that they would stay in good integrity until we got around to using them. That didn't work so well. Ultimately, we ended up having to borrow a bone saw from anatomy and physiology in order to actually cut the sodium block. So soft is relative. Soft in comparison to, say, steel, soft perhaps in comparison to copper, not soft necessarily in comparison to other things. And that bottom line there, they react with water, violently, in fact. If you jump on YouTube at some point and you put in the search bar something along the lines of sodium, water, and fraternity, you will see two guys who kind of deserve a Darwin Award, who somehow acquired a very large chunk of sodium and a galvanized steel bucket and pitch the sodium into a bucket full of water on the front line of their fraternity house, and it explodes. Which kind of demonstrates the violence of the reaction, but yeah, it's a pretty dangerous thing to do. All right, let's hop over to the next column. Beryllium, magnesium, calcium, strontium, barium, and radium, radium being radioactive. These have a similar name for their group called the alkaline earth metals. Now, one of the things that's true about these is as they oxidize, they produce a powdery oxide substance, which if you try to dissolve it in water will give you a solution that is very basic in its pH, meaning above 7. Some other things that are also true, FA-18s that are the general fighter planes that are on the carriers around here are made predominantly of magnesium. If your FA-18 catches on fire, you can't put it out. Basically, and I've been told by this by a couple of Navy students, that there is usually a bulldozer on the aircraft carrier such that if your fighter aircraft catches on fire, you push all $45 million of it overboard, because magnesium is not capable of being extinguished. It will even burn underwater. Okay. So some interesting trivia that kind of goes along with some of this. Let's hop across the big gap there in the middle of the periodic table over to almost the far right-hand edge. Fluorine, chlorine, bromine, and iodine. And yes, there is one more element at the bottom, which we're going to kind of temporarily ignore, which is known as astatine, a very rare and radioactive element that doesn't have a lot of uses. Group 7 are known as the halogens. You almost never find them in their pure state in nature. They are usually in their ionized state. Fluoride, chloride, bromide, and iodide. Things that are attached to other elements when you have them in compounds. Things like sodium chloride, table salt. Okay, sodium chloride is going to be something, excuse me, that has a metal plus a non-metal. And then we jump over to the final right-hand column, which is the noble gases. We have helium at the top, and they go from helium, neon, argon, krypton, xenon, back down to the radioactive end of things, which is the radon. Most of those are very, very non-reactive. You will occasionally later see a few compounds that contain krypton or xenon, not the ones that are higher up on the table. More trivia. The searchlight that is on the top of the Luxor in Las Vegas is a xenon-based light because it allows it to burn at a much hotter temperature without degrading and needing to be replaced. It also prevents the airplanes that are taking off from McLaren Airport, which is only about a mile away, from hitting the pyramid on the way out of the airport. So it has uses. If you look at the periodic table in your lab book, you will notice that there is a sort of staircase that goes down one side of your periodic table that's in your lab book. We'll see if this shows up okay. See the dark line? Okay. Makes this little staircase that kind of goes down toward the far right-hand corner there. Indicating where the staircase is actually serves a purpose. Anything that is above the staircase is a metal. There are many, many, many more metals than there are non-metals. And actually, I said that backwards. The stuff in the upper right-hand corner is the non-metals. Everything else is the metals. There are still way more metals than non-metals. That little squash downward section in the center of the periodic table are known as the transition metals. Those bottom two stripes that we mentioned earlier are known as lanthanides and actinides. If you look at the little asterisks that are indicate, like here's, you go across the table and then you jump down to where those stripes are, you will note that those are the elements where the jump occurs. That lanthanide, which is number 57 on the periodic table, is where it then jumps down to cerium, which is number 58. And number 89, which is actinium, jumps down to thorium, which is number 90. So since there are lots and lots and lots of metals, there are certain things that they tend to have in common. Now, granted, they do not do all of these equally well. They do all conduct heat and electricity, but copper wiring, that's a cool deal. Okay, you probably wouldn't want to make wiring out of cesium. That would be problematic at best. They are all malleable. Malleable means able to be flattened. So gold foil, aluminum foil, those are things that actually flatten out into a thin sheet with relative ease. On the other hand, if you tried to do it with something like mercury, you'd be in trouble. Ductile is a related characteristic, which means it can be drawn out into a wire. Again, copper wiring, aluminum wiring's not awful. You could make ironing out of iron wiring steel. Trying to do it out of something like zirconium, not so easy. Niobium, on the other hand, niobium wire actually works pretty well. And they are lustrous. Lustrous meaning shiny. This, however, is somewhat dependent on their purity. If you have a sample of a metal that is essentially 100% pure, they tend to be shiny. And in fact, most of them are kind of silvery in color. However, as they react with other substances, they become dull and create coatings. Now, the non-metals, they don't have a whole lot in common. There's a couple of general statements we can say about them. Most of them are either liquids or gases. If you look at the color-coded table that is in your textbook, it makes it a little more obvious to see which ones are gases and which ones are liquids. One of these specific liquids being bromine. Bromine is a liquid in its pure form. In fact, a very caustic liquid. There's three elements that kind of occur right along the staircase: silicon, germanium, and arsenic. Hearing those three names together hopefully prompts a little bit of a connection. These are elements that are primarily used in computer chips because they have some of the characteristics of metals and some of the characteristics of the non-metals. Now, one of the things that's also you may run across, there are some other textbooks that will claim that you should throw boron in with the semi-metals. There are a few textbooks that will claim you should throw antimony in along with the semi-metals. I am sticking with the ones that aren't up for debate. The silicon, the germanium, and the arsenic, those are guaranteed to be semi-metals / metalloids. And then we kind of revisit for just a moment here that whole biological elements idea. Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. All right. Now we begin to head in the direction of nomenclature. Nomenclature is very much like learning a foreign language. There are conjugation rules. When you learn a foreign language, there are nouns, there are verbs. If you take something that's not English, sometimes the the nouns have gender, and you have to make sure your articles agree with the gender of your noun. And sometimes you have to find out that your adjectives must agree with the gender of your noun. All of those are thoughts that sort of apply in similar ways to the rules of nomenclature. Some of it is memory. Some of it is application. Like I said, even though we are doing this electronically, under more normal circumstances, you are required to memorize the names of the first 100 elements. Obviously, in doing this electronically, you have access to the periodic table with the names on it. So we approach this from a slightly different point of view, but I will say that the more familiar you are with those element names, the easier you will find beginning to put the pieces together. So we are going to start with the smallest and simplest form of a molecule. Take two of the same thing and stick them together. They are known as diatomic molecules. There's a bunch of gases that prefer to occur this way. And I'll call it a mnemonic, okay? A way to sort of stick in your brain which ones like to do this as much as possible. So old brown finch. The O represents oxygen. Oxygen gas very seldom occurs as single atoms of oxygen, and also only rarely occurs as an O3 molecule, which is known as ozone. Bromine, halogen, also likes to be in pairs, as well as fluorine and iodine. So the brown is the Br for bromine. The F of finch is the fluorine. Iodine, the I in finch. N is nitrogen. C, however, is not carbon. C is a halogen, chlorine. And you have one final element there, the H at the end of finch, which is hydrogen. So these 7 elements you will see quite frequently as we eventually progress from molecules into reactions. You will see most of these elements occur in their diatomic form. So the beginning part of the chapter, we focused on the idea that we wanted the number of protons and the number of electrons to match and have no leftovers. So let me go back and pick on an element, and I'm going to hop over to my whiteboard to do this. Let's pick on manganese. All right. So Mn, okay, also known as manganese. It is atomic number 25. And one of the isotopes has a mass of 55. All right. So therefore, based upon this idea of your positive bits have to equal your negative bits, you would have, oops, it's supposed to be 25 protons. You would have 25 electrons. And then you are going to have to do 55 minus 25 to figure out how many neutrons you have. And yeah, that was supposed to be an N, not an M. So 55 minus 25 will give you 30 neutrons. So think about this in terms of if you are dealing with isotopes, because here we are about to change the rules of the game in that we are going to look at things that do not have the same number of protons and neutrons, or protons and electrons. All right, so let's take about a 10-minute break, and then we're going to come back and talk about cations and anions. So, yeah, my kids are around in the back. I'm trying to figure out how to, I have a bunch of ions, okay, which is why I was waving this in front of the camera here. This is one of the things I miss about like being able to like use a board, a real actual board, easily the way I do on campus is these are ions, okay, and they actually have magnets on the back, and so I can create molecules and help with the visual end of things. So I'm going to try to do it on the whiteboard, but it's not as easy as it should be. Yes, my cat is trying to chew on my my cat is trying to chew on my cat ions.
They're called cat ions because they're positive.
Yeah. Bad chemistry jokes. All right. Let me go back to screen share here. All right. We are going to talk about the things that do not have equal numbers of protons and electrons. If you have a charge, be it positive or negative, they are known as ions. And therefore, you can divide it into two halves. Do not call them cations. Okay, they are known as cations. It is pronounced as if it were two separate words. Anions are the other kind. So the cations are the positive ones, more brain tricks. A plus sign resembles the letter T that is in your word cation. And so that's one of the ways you can kind of connect those two ideas together in your brain. What makes things positive? Loss of electrons. Because you can't gain protons. In the world of normal, average, everyday chemistry that doesn't involve nuclear accelerators, you can't do anything about the protons. They're there in the nucleus and they just sit there. But you can reveal them by stealing away electrons. So let's pick on lithium. Lithium has 3 protons because it's number 3 on the periodic table. And if you steal one of the electrons, you will end up with a lithium ion, and the electron goes to live with somebody else. A calcium atom has 20 protons because it's number 20 on the periodic table. Therefore, it has a tendency to lose 2 of its electrons and have only 18 left. And the 2 positive charges that used to be covered up by those 2 electrons now kind of shine through. How about the opposite end of it? What about the elements that like to do the stealing? How about fluorine? Fluorine has 9 protons and originally has 9 electrons, but it likes to go out and steal one from somebody. And this becomes an F minus. Oxygen likes to steal 2 electrons. Oxygen has 8 protons. If it goes out and steals 2 more, it now has 10. And now it has a -2 charge on it. As atoms change from neutral elements into ions, there are some rules that go along with this. This is the beginning of the rule part for the nomenclature. Things that are cations don't have a lot of change to them. You take the name of the element and you just sort of tack the word ion on as a second word. Sodium ion, calcium ion. Anions get conjugated. You remove part of their name and you attach an IDE ending. F minus becomes fluoride. Oxygen loses most of its letters and pairs it all the way down to the O, the X, and then you put the IDE ending on it. So not oxygen, it's supposed to be oxide. Nitride, bromide, phosphide, sulfide. All of those are ones you will be seeing. If you look across the periodic table and you skip that chunk in the middle that has all the transition elements, there is a pattern to this. Back over to my whiteboard. All right, so remember this is your profile of your periodic table, and it kind of goes like this. All right, first column, +1. That's everything in the hydrogen column likes to be +1s when they become ions. Next column, alkaline earth metals rather. They like to be +2s. You skip all this stuff in the middle. I didn't quite leave myself enough room here, but you get +3s, plus or -4, -3, and it would help my little pencil thing work better. -2, -1, which is actually the halogen column, and the zeros that are over here. Let me flop back over to my other document. So look at the pattern here. +1, +2, +3. Carbon is the make or break it point. Okay. Once you hit the carbon column, you hit the spot of, well, is it easier to steal 4 electrons or is it easier to give 4 electrons away? And in fact, carbon and silicon often do neither. They like to share. Nitrogen column -3, oxygen column -2. All the halogens are -1s. Remember when I said the noble gases are very unreactive. They hate everybody. They really pretty much don't like to be part of a molecule, so they hardly ever have a charge at all. Now, transition metals, we can make a global statement as they are always positively charged, but the further we dig into this, the more we see that their charges kind of vary. And they vary depending upon what kind of a partner they have in a molecule. If you are creating a molecule, specifically referred to as an ionic compound, all of your cations and all of your anions should cancel out so that there are no leftovers. And we are going to call this a binary ionic compound. Okay. It does not necessarily mean that there's only 2 elements, or there's only 2 atoms. It means there's 2 elements. And I obviously misspelled fluorine. There, it's fixed. If you want to combine sodium and fluorine, So sodium in the first column of the periodic table usually loses an electron. Fluorine likes to steal electrons. Therefore, when you stick the two of them together, you get a molecule which has no charges written in it. Once your two ions stick together, there are no leftovers. I'm going to attempt to show you my little toys. At least it helps a little bit with the visual. So how about potassium? Potassium, same column as sodium. Note, it has one pointy bit. Okay, that's to remind you that it has a +1 charge. All right, here's my chlorine. My chlorine has one cutout. If I stick them together, and I hold them at the right angle here, you can kind of see one positive and one negative cancels each other out, which is part of the reason why you see no charges written inside your molecules. As we progress further and further into this chapter and on into upcoming chapters, do not write charges inside full molecules. They are canceled out. What if it was not just one electron that was having it's stealing or it's giving away? What if you had two electrons being traded? So I picked on magnesium. Magnesium's an alkaline earth metal. It likes to be +2. Oxygen's the column that likes to be -2. So if you stick one of each together, again, you have no leftovers. You have MgO. That means you have one atom of each element and no charges left over. Strontium. Okay, strontium's in the same column as magnesium. So it has 2 points on it. Here's my oxygen. Let's see if I can merge them here correctly. That's not too bad. You can see that a single atom of strontium basically fits into a single atom of oxygen and gives you a neutral molecule. What if your numbers don't match? I'm going to pick on aluminum and oxygen. So aluminum has a +3 charge in its ionized form. Oxygen has a -2 charge. You can do a couple of different methods to kind of make this idea sort of swap out. Back to my whiteboard again. All right, what if I do this? Okay, we're going to take aluminum and put the +3 on it. And over here, we're going to take my oxygen, and it's -2. So if I take the 3 and I turn it into a subscript on the other element, and I take the 2 part of this one and I swap it over here, you will get Al2O3. This is your neutral molecule. That's not necessarily the only way to think about it. And there is a little bit of a hang up if you have two separate even numbers, because then you have to worry about least common multiple kind of thing. Here's another method of approach. What two numbers do 2 and 3 both divide into? Well, 6. So I need to have a way to have 6 positives and 6 negatives. And so I wrote them out here kind of like a math problem. If you take your +3 and your next +3, then you have your 6 positives. If you have O minus 2, O minus 2, and O minus 2, you get 6 negatives. And once you match those together, there are no leftovers. That is the goal. When you are creating molecules all the way up until we get to much later in the semester, you are looking at situations where your molecule must have a neutral charge. So thinking about magnesium and bromine. Magnesium likes to be +2. We saw that above. Bromine is a halogen. It is in the -1 column. And so in order to make this be a neutral molecule, I can't have just one magnesium and one bromine. I actually need to have 2 bromines to make this work. Otherwise, it would not be neutral. Now we begin to progress toward the, okay, we made some molecules, and we know some of the rules for naming of ions. So we need to start pulling some more pieces together. Oops, and I went a little bit too high up the page there. So that thing I just created, okay? Mg and Br2, which has 3 atoms, but 2 of them are the same thing. When I name it, name the metal part, which is the cation part, first. Then you name the anion, and the anion must be conjugated. Okay, it must have that IDE ending in it. So magnesium bromide, you cannot call it dibromide. You cannot call it 2-bromide. You cannot call it bromide 2. There are only 2 words to the name of this molecule: magnesium and bromide. The knowledge that there are 2 atoms of bromide in this molecule is supposed to be implied knowledge. AlCl3. Yeah, you've got 1 aluminum and 3 chlorines, but we must call it aluminum chloride. No 3s, no tris, no additional suffixes or middle words, just aluminum chloride. The one that I showed you, the 2 pieces stuck together there. SRS, strontium sulfide. And my molecule that had the evens and the odds, Al2O3, is aluminum oxide. Do not try to call it dialuminum trioxide. That is so very wrong. As long as you have a metal that I'm going to loosely refer to as the normal metals, to differentiate them from the transition metals, along with a non-metal, the how many you have has no effect on the name. But now we need to progress in the direction of the transition metals. Transition metals often have kind of an either or. It's either that charge or it's this charge. And there is no pattern. There is no way you can look at the periodic table and go, oh, well, these are the +2s and those are the +4s. You have to look at a full molecule if you are not told what the charge is. They're all positive, but they are somewhat fickle. They adopt the charge eventually of their partner. We are going to focus primarily on the Roman numeral system, which is also known as the stock system. But I will also spend a little bit of time talking about the old system, which also I refer to as the ich and us system, because it has to do with suffixes. So I gave you a couple to start you off here. Cu+2. Because that particular version of copper has a little +2 written beside it, we are going to designate it as the copper 2 version. There is another version. Lead has, in this case, the designation lead 4 because it has a +4 written next to it. Tin 2 because it's Sn+2. Okay, now we kind of circle back to but there's 2 versions of each of these. At least 2 and occasionally 3. We're mostly going to focus on the 2 version. Iron has 2 options. Iron comes in +2s and comes in +3s. If we stick with the stock, the Roman numeral system, you can just literally write the Roman numerals next to the word. But there was a reason why I spent a little time talking about the Greek and Latin roots at the beginning of this chapter. Look at the older naming system. If your career path is headed into the medical field, forget the stock system in terms of your career path, because the medical community almost always uses the older naming system. For some reason, it's a hangover, okay, from the way medicine evolved from a historical point of view. And they stick with the Greek and Latin roots as well as the suffix endings. So iron 2 is known as ferrous. Iron 3 is ferric. Lead 2 is plummus. And lead 4 is plummic. So this is kind of why I referred to it as the ich and us system, because look at those suffixes. There is a rule, okay? But I will confess, the rule doesn't actually help you an awful lot, because the rule is partially dependent upon memory. We can say the rule, and the rule doesn't get violated. Like I said, it does work. It just, if you don't have some clue that +2 equates to OUS, if you're talking about iron, obviously there are options that are different for other elements. So the higher charge gets the ich ending, and the lower charge gets the us ending, OUS specifically. All of the ones here that I've shown you at the top of this particular page don't have any anions stuck to them. They're all just metal ions, metal cations. That's not usually the way we see them, not very often. Usually we see these metals as part of a bigger molecule that has anions involved. And so Let me pick on the iron, and I'm going to stick a couple of bromines on the end of it. Now, in order to figure out, do I have ferrous or ferric? Do I have iron 2 or do I have iron 3? Start on the right-hand side of the molecule. Start on the anion side. Figure out what that charge is. In this case, the bromine is a -1. Multiply it by how many you have. Okay, I have a subscript of 2, so -1 times 2 gives me -2. In order to make sure that my molecule is neutral, my iron's got to be a +2. Otherwise, it doesn't match out. So if I use the stock system, this is iron 2 bromide. If I use the older system, it is known as ferrous bromide. Do not mix and match. If you use the word ferrous, don't use a Roman numeral. Okay, the two are two entirely different systems. Cobalt and sulfur. Now, sulfur is underneath oxygen on the periodic table. So it has a -2 charge. I have 3 of them in this molecule. So I have 6 negatives. But I've got 2 cobalt atoms. Take your 6 positives that they must actually add up to be, divide it in half, and that means that cobalt in this particular case is +3. So you have 1 cobalt 3 cation, and then you have a second cobalt 3 cation. I can name it cobalt 3 sulfide, or I can name it cobaltic sulfide. How about tin? Tin, again, sort of harking back to one of those Latin-based names, which used to be known as stannum. My oxygen is -2. I've got 2 of them. So there are 4 negatives in this molecule. And I only have 1 atom of tin. It must be the +4 version. So I have tin 4 oxide, or I can call it stannic oxide. Don't mix and match. Don't call it stannic 4, okay? Stannic means that it has a +4 charge. Have a look at this one. AuCl3. More ridiculous trivia. So if you are a James Bond fan, he has an arch enemy known as Goldfinger. If you pay attention and or you read the books, Goldfinger's first name is Auric. So kind of science puns to a degree, because if I look at this molecule, which has an atom of gold in it, and then it has 3 Cl minuses, I've got a gold 3 chloride molecule. Or if I go back to the Roman system, auric chloride. There is such a thing as ores chloride. Gold occasionally will occur in a +1 version, although usually that particular version is somewhat more rare than the +3 version. So there are 2 transition metals that, it looks like I probably spelled conspicuously wrong, that don't have an either or, okay? They only have 1 charge and it never changes. we will tend to go ahead and keep the Roman numeral that goes with them, even though it's not strictly necessary. But back to that whole medical community thing, if you see something labeled silver nitrate, which is often used to stop bloody noses and things like that in the ER, it's not going to be labeled silver 1 nitrate. It's just labeled silver nitrate. They don't put the Roman numerals in it. Silver is always and forever +1. There is no other version of silver. The same is true for zinc. Zinc is always and forever +2. It does not have an alternate version. If you buy, if you're one of those people who sunburns really easily and you buy the white stuff for your nose to take to the beach in the wintertime, in summertime, that's labeled zinc oxide, no, there's no Roman numeral in it. It's not zinc 2 oxide, it's just labeled zinc oxide. So I gave you another example here for the silver. Silver chloride, okay, AgCl. Now, I think your textbook is relatively consistent in throwing the Roman numerals in for silver and zinc in even when they are not strictly needed. I'm not sure that your lab book is quite as consistent. I think perhaps there are a couple of instances in the lab book where it does not put the Roman numeral 1 in with the silver. All right, now we're going to switch gears just a little bit. All of the stuff we've been looking at in this sort of center part of chapter 2 has pretty much involved taking a metal and sticking it to a non-metal. There is another set of binary compounds that involves 2 nonmetals. And yes, there is a way to combine 2 metals. They are known as amalgams, and that is a much higher level of chemistry than we are going to address. So kind of pretend that that's not a possibility. We're going to focus on the 2 nonmetals variety. So we're going to make some assumptions that are loosely true in a way where right at the moment, you kind of have to take it on faith. Okay, we'll talk about why it's true the way it is more later. But for the moment, just go, okay, yeah, we'll just take the rule as is. Assume that the first element, meaning the left-hand one, is positive, even if according to where you looked it up on the periodic table, it looks like it should actually be a negative thing. So pretend it's positive anyway. But then you can go ahead and pretend the second one is negative. We're actually going to throw a prefix system in. These are kind of, sort of the prefixes that you run across taking geometry class to a degree. Mono for 1, di for 2, b as in boy, okay, to give you bi actually means something different in chemistry. We'll eventually get around to that. Tri for 3, like a tricycle. But they don't use quad, they use tetra, as in tetrahedral. And then you get more sort of traditional geometry prefixes: penta, hexa, hepta, octa, nona, and deca. Yeah, there are actually some prefixes that go above deca. We don't usually address them in freshman chemistry. The other hiccup to this naming set of rules is you're not allowed to use the mono prefix on the first left-hand element. So I have some examples here to kind of hopefully pull some stuff together here. CCl4. We've got 1 atom of carbon and we've got 4 atoms of chlorine. We're going to call it carbon tetrachloride. Don't call it monocarbon. This is the application of that rule that's listed above there. If there is only a single atom of the left-hand element, mono does not get used. Carbon tetrachloride is a liquid, somewhat carcinogenic, that does have some industrial uses. It is referred to as a nonpolar solvent. Later on down the line, we'll talk more about what nonpolar means. CO. This is not a cobalt atom. This is a carbon connected to an oxygen. Carbon monoxide. Okay, they deleted one of the O's to make it easier to pronounce. So if you have a carbon monoxide detector in your house, okay, carbon monoxide is one of the things that is part of your car exhaust. This is why you don't run your car in a closed garage, okay? Because then you have to worry about carbon monoxide poisoning. And if you say the word carbon monoxide to most people, they will go, oh, that'll kill you. But they probably can't give you even a clue as to why it's called carbon monoxide. This is the reason, okay? Carbon dioxide, the stuff that we as mammals exhale, 1 carbon, 2 oxygens. And I have a few more that I threw in here. Sometimes you will have multiples of the first element. Then you are allowed to use prefixes. N2O5, dinitrogen pentoxide. Again, they are deleting one of the vowels to make it a little smoother to pronounce, instead of calling it pentaoxide. Here is one of the few molecules that you will see that actually contains a noble gas. We have xenon on the front of this molecule. Xenon's a nonmetal. XeF6, xenon hexafluoride. Here's a less common molecule, oxygen difluoride. 1 oxygen, 2 fluorines. So up to this point, have basically been dealing with things that have 2 elements. However, that is not the sum total of chemistry, reality, and in terms of nomenclature. There are quite a few molecules that have more than 2 elements involved. So now we begin to head in the direction of multiple elements combined together, but they behave like they were a single unit. So this is how I like to describe polyatomics. They have several atoms bound together. They behave as if they were a single element, and they also have 1 single charge that is applied to the whole collection. There is a whole page of them in your textbook. I believe I quoted the correct page number there, which is page 62. There is also an entire really expanded page in your lab book. Let me look up the lab book number. Page 99 in your lab book. So this gives you lots of places to look up the resources. All right, more rules that honestly don't actually help you. Part of this is memory, part of this is understanding the system. Most of these things that you see have oxygen atoms in them. Take a look at the top two there. We have SO4 minus 2 and OH minus. Each of those is a collection of atoms that has a charge written off to one side, and they have one name. We have sulfate and hydroxide. But one of the things that's also true about these collections or groups of oxyanions is some of them occur in pairs, twos, and some of them occur in fours. So let's talk about the ones that occur in twos to start with. The ones that occur in twos, okay, the blanket rule says the one with the smaller number of oxygens gets an ITE ending, and the one with the larger gets an ATE ending. So I gave you NO2 and NO3. And let me add this in here, because then there's actually more to this. Okay, look from the one above. So SO3 minus 2 gets known as sulfite. And SO4, oops, I went too far across the page there. Yeah. I kind of hosed the negative sign there. All right, so look at these pairs. NO2 is nitrate, NO3 is, and actually I said that backwards. NO2 is nitrite, NO3 is nitrate. SO3 is sulfite and SO4 is sulfate. This is one of the reasons why I usually state pretty blanketly, the rules don't actually help, because people are tempted to say, oh, 2 oxygens makes an ITE and 3 oxygens makes an ATE. Not true. The rule does get obeyed, okay? The one with the smaller number of oxygens has the ITE, and the one with the larger number of oxygens gets the ATE. But larger and smaller are relative. So part of it is learning the pattern. Sometimes you have sets of 4, and this is especially true with the halogens. So a little bit back to Latin stuff here. Hypo means under, as in hypodermic needle, goes under your skin. Per, as a Latin root, means more or above. So in sets of 4, you have hypo something, ite. The ite and the ate are in the middle, and then the per ate is at the bottom. So I picked on chlorine, but you can actually do it for any of the 4 halogens. Hypochlorite, HC or ClO minus. ClO2 minus is just chlorite without the hypo part. Chlorate has ClO3, and perchlorate is ClO4. Note, every single one of those has the same charge. So the charge actually has no effect upon the name. It has to do with the number of oxygens in the pattern. Naming of polyatomics really is a lot of memory, or a lot of interpreting how to apply the data. So I gave you a couple more examples here, and there's more examples in the book. CaOH2. Now, if you have more than one polyatomic, you must put parentheses around it. This is kind of looks like an algebra rule. We've got calcium hydroxide. Don't call it calcium 2 because it's not a transition metal. Don't call it dihydroxide because it's not a non-metal pair. It's just calcium hydroxide. Na3PO4. Sodium phosphate, because PO4 is known as phosphate. FeSO4. Okay, we got to figure out which version of iron we're talking about here. When you look up SO4 and note that it has a -2 charge, then you can interpret that since I have a single atom of iron, I have iron 2 sulfate. If I go back to the older system, this is ferrous sulfate. Okay, there's one little extra fiddle to this that is involving peroxide. And you will not see a lot of peroxides. Peroxides are actually kind of rare. If you have a metal from the first column of the periodic table, an alkali metal, then it's a peroxide, not a dioxide. All right, this leaves us one little section of naming rules left to cover. Plus, I also want to spend some time on Tuesday giving you some additional examples. We're also heading toward the next cycle for lab. Let me twist around backwards here and grab my lab book. So the next cycle for lab involves the people that I have on Monday, which is the 7th, doing separation of a mixture. That is your face-to-face lab. And then I will see the Wednesday people on the 9th. But one of the things that everybody is then doing as part of the rotation is the nomenclature lab, which is loaded to Canvas. Make sure you download the homework for this chapter, which is not due yet, but will probably be due on Thursday. Because like I said, I want to give you a few additional examples and cover the last set of rules. But the lab report for Dry Lab 2, which is the nomenclature lab, has a file. When you log on to Canvas, and it gives you information on the page and on the module, there is a document, okay? There's a Word document. You are only doing the problems that are specified by the document. Yes, there are a lot, but not as many as in the lab book, okay? There are 120 in the document. There's actually about 400 in the lab book. So this is why we're not doing all of them. We're only doing 30%. And you will probably view this as a head-pounding event, kind of a little bit literally, but it works. Okay, part of the reason for doing this particular lab the way we do it is by doing about 100 or so of them, once you work your way through all of those sets, it fosters patterning in your brain of realizing that certain things linked together certain ways have certain pattern in the naming. It's all about the pattern recognition as well as the rules. So this is kind of why we approach this as a department. We all do the same lab. So you have a lot of naming stuff to work on here over the next week or so. My advice is do as much of the homework for chapter 2 as you can this weekend, so you don't have it all to do next Tuesday, Wednesday. See if you can get the majority of it done this weekend so that you'll only have a little bit left to do after our lecture on Tuesday. Because like I said, homework for chapter 2 will probably end up doing 1 week from tonight. So it'll probably end up being due next Thursday. Questions? And I will also talk some more about labby things probably on Tuesday, as well as finishing up the tail end of the chapter 2 notes.
So Tuesday we'll finish chapter 2 and then we'll start chapter 3?
Yes.
Okay.
And what this will probably mean, actually, let me pop open my Google Calendar here to look at. Because, of course, this is a much shorter semester, being a summer semester, it means that the first test, which is comprised of chapters 1 and 2, may end up being the weekend of the 12th and 13th. I have few, it's like during the 16-week semester, I have a few more weekends to choose from because I prefer to give tests over the weekend so that you have from Friday morning until Monday at midnight to do the test. I'll probably, even though I'm probably going to have homework due on Thursday, I will probably post the answer key to the homework the next morning so that you can refer to it prior to taking that first test. Like I said, we have fewer weekends to choose from. We only have 9 weekends to choose from in terms of when I give tests. But I know that people have all sorts of wonky job scenarios in terms of scheduling. So I like to try to give these because obviously you're doing them on Canvas. I try to make it so that the tests occur over the weekend window. And that way people have more ability to choose what time of day or which day they take the test. They can either take it at the beginning of the time allotment, which is like Friday night, or they can take it at the end of the time allotment, which is usually Monday morning. That way, if you have weekend job stuff, you also have some other available time periods that you can take your test. Usually the test is a 4-hour time window. Once you start it, you can't stop it in the middle. Basically, once you start it, you have 4 hours and you're done. And I'll talk more about that next Tuesday also. But we are approaching the end of what will be on that first test, chapters 1 and 2. Other questions? Otherwise, I will see some of you on Monday.
All right, thank you.
Have a
John.
good weekend. Yeah.